Good afternoon, YouTubers. Today we're going to be studying what are the forces involved when a car is in a bank curve like this. So the car is, you're driving your car and you find out that you're like in a racing or you are racing and there's an angle that will help you to stay within their bank curve. So there are many questions here, and one of them is how you analyze the forces, because there's a centripetal force that is pulling the car toward the center based on a given diameter. In this case, is a given radius from the center of the car going that way. But as that is happening and you are driving, at a certain speed, there's a tendency for the car to to try to get to move out of the road, but friction will take over from there, and the friction will be like this coming down. So you have a force here called friction, but then as shown here you have a force just because of the car weight that is going to be W. And on this W, let's say that the GC is somewhere here on the car, so this will start to look like this, but then you have a normal force that will start to look like this going through the GC. I'm gonna draw like this because the idea is that that normal force I'm gonna call Fn. So right now, as you can see, I have identified what is the normal force from the center of gravity, the friction force somewhere here in the inclined plane at a given theta angle, and always the question here is what's the maximum velocity, I would say Vmax, that you can take without getting out of the bank, right? So definitely this will help the car to stay within the bank curve because you have an angle here, but we're going to demonstrate what will be the maximum speed for the car and still stay within the bank at a given friction mu s here at the given angle shown here. So we have, this is the big deal, this is the big question, what is the Vmax? But then the parameters that we're going to have is mu s and w. Those are the two parameters that we're going to work on this just to get that maximum speed. Now with that said, so we have the car, we have a W here, and this is angle theta. This angle here between this guy and this guy will be also theta. Now if I keep drawing like this with this type of line, the idea is that when we do the force balance here, check what is on X, check what is on Y. It's important that we label what's going to be on X and what's going to be on Y, because sometimes when we do, like for example, if we do let's say that there's a block here and that block is sliding down, typically as this block sliding down, you put the friction force like this, let's call that EFF. But then what you really want is to break the other force, like for example the force of this coming down between at the angle here theta, and this is theta, so you stay basically within X and Y, but check the Y and the X for this block is following the angle theta that is shown here. On the other hand, for the car, it does not work like that because of this acceleration that is right here. That acceleration is on the x-axis, the way it's shown here. So the forces that I'm showing here, like Fn and Ff, need to be broken down, this y and x, so that we can work the problem based on this centripetal acceleration. So with that said, let's say for example, let's find out what are the forces, for example, in y. So just to get to understand the forces now, the force balance, let's start with the y and the y axis, this axis here, and so that will be the sum of all the forces on the y-axis, positive up, equal. Now the car would not be floating or moving up, or like floating from the road, so that means that there's not going to be any acceleration on the y-axis. That's going to be 0, equal. Then the only thing left is if I decompose Fn in terms of the y-axis here, and that's the y, so that means up is Fn cosine of theta, breaking this into this. Now what happened with FF, which is the other force? Well, FF will have two components, one going that way and one coming down. At this point, see, I'm doing a balance on Fy, so that would be FF minus, because it's coming down, minus FF times sine of theta. So I'm breaking this into this. That's where the sine theta comes from there. Now W is the last force, and that's coming down as well. So we got that, minus W. But then what is FF? FF by definition is the normal force. The normal force here, this Fn, multiplied by the friction factor, that's mu. And let's call it mu s. And what we have this equation. Let's again, Fn cosine of theta minus FF, but that's Fn mu s times sine of theta minus W equals 0. So finally I can break this for Fn and find out that Fn as a common factor is cosine of theta minus mu s sine of theta equal W. It's going to be positive. Finally Fn equal W cosine of theta minus mu s sine of theta. There we go. So that's what we got. That's how we're going to break the normal force within this axis here, y and x. Alright, so we got that. Now what happened in the x direction? And that's the important part. On the x direction, and in this direction we have friction going that way, but we also have Fn going that way as well. So we got two components, this one and that one. So, and those two components are allowing this car to accelerate with this normal acceleration called An, going that way. So that means that the FF in the x direction plus Fn in the x direction must be equal to the mass of the car times the normal acceleration called An. Alright, so what is FFX? Well, that is whatever definition I have for FF, which is normal times mu s. So let's do that. Fn mu s times, since I'm breaking this on this, so that would be cosine of theta plus, now what's happening here, the Fn I'm breaking into this, so that would be sine of Fn plus sine of theta, and that has to be equal m. Now, but what is normal acceleration in terms of tangential velocity on the car? That would be b squared over r. So Fn is a factor here, we can take that Fn out, and eventually we end up with mu s cosine of theta plus sine of theta equal m bt squared over r. And now Fn is this definition here, but W, if you remember that, that's going to be mg. So we end up having mg over cosine of theta minus mu s sine of theta multiplied by this definition here. I'm going to put it here, so that's going to be mu s cosine of theta plus sine of theta equal m bt squared over r. The m cancel out, kind of nice, and we end up with something like this. So mu s cosine of theta plus sine of theta divided by cosine of theta minus mu s sine of theta, and then that multiplied by g, and that has to be equal to bt, the tangential velocity square, over r. So basically, if I put this in terms of the tangential velocity, that would be b equal square root of g times r, let's put a big parenthesis here, mu s cosine of theta plus sine of theta divided by cosine of theta minus mu s sine of theta, close parenthesis here, the square root of that, and that's our in this case maximum tangential velocity. So that's the maximum tangential velocity is defined by this equation as shown here. Now few things here and there. Let's say that mu s is 0. That kind of simplify this very quickly, because it will end up like bt equal the square root of g times r, g being the acceleration, and we end up with sine of theta over cosine of theta, and so bt equal gr times the tangent of theta, and we're done. So this is a simplification in the case of theta, in case of mu equals 0. So you depend, in order to maintain the car within the bend curve, that if there's no friction, you will have to have certain angle to maintain the car within the bend curve. That's what this is saying. No friction is going to be hard for that car to stay there, and but I mean, so you got both results here. One that depend on both the angle, static friction. What will happen now that I'm entertaining this? What will happen if theta is 0? If theta is 0, there's no angle, so this is gone, this is gone, all the signs are gone, and you end up with mu s cosine of theta, and this is gonna cancel out. So you end up, in the particular case that theta equals 0, you end up that also bt equal the square root of gr mu. Interesting. This result is basically like you have a disk and you have an object here, and that object is at a certain distance from the center r. As this disk is spinning, it will create a tangential velocity. So in order to maintain that object right, moving along a path here, then basically you have to have certain friction within the object and the disk, otherwise it will be removed from the spinning disk. And so for this case, since I know bt, then if I want to know what is the angular of rotation here, the angular speed, then angular speed is going to be then v over r. So that's how fast this is moving, and in order to maintain this object within the disk, then you have to have this property here, so you cannot spin or move, or the angular speed cannot be higher than the value dictated here. So that's kind of a summary of what's happening on the two extreme here. One is when mu s equals 0, you end up with this, but on the other hand, if theta equals 0, you end up with this. Anything within like theta is greater than 0 and mu s is greater than 0, then you have to use the full equation here just to determine that bt. Remember that speed is maximum speed. This one here is bt, I would say maximum, because otherwise the car will, get out of the bank and it will be over. So that's one of the simple analysis that you can do within the car. And basically, let's see something here. So again, remember the two main forces here involved is friction, but since we don't want the car to get out of the bank curve, so friction is down, force of friction. But then you also have to break the normal force here, that's Fn, going that way, but that Fn has to be break in two forces. That will be one, and this will be the second. So you have to break like this on these two forces, and FF has to be broke as well into forces, one on the X and one down. So if you do that, then that's how we derive to those to the equation shown here, like this one, or this one, based that we don't want the car to bank out from the curve. Now that's perfect, and let's do this. So we start a new page here. Let's say that everything's back again the same way, the same it was, but now the car is so slow, that the car will start to be kind of a fall down. Not that it will get out, but not fall down. So if that's happened, then check the direction of friction. Friction will be that one, that way. We'll go, to avoid that the car falls down, friction has to be in that direction, up. So with that said, then how can we work the minimum speed to sustain the car within the bank curve? So that's another story, right? Before we calculate Vmax, now we're going to calculate Vmin, or minimum speed. That's what we're looking at. Now to do that, it's pretty much the same game, except now we go here and we go here for the normal force, that's Fn, but then we need to work the detail of these forces. One of them is obviously this one here, and this one here, and then one here. So we have Fn, we need to break it on this direction here, on the Y direction, and one in the X direction. Remember that has to be done due to this, because that's right within the X direction as shown on this coordinate. So what's happening on the Y, then we need to think what's happening with the friction. Well, the friction is, let me break it here as well. Friction is going like that, so we have one going up, and this is the angle. That angle is the same as this one, that's theta. But then we have another one that is going in the X direction, but it's going this direction, and this is F due to friction. So we have our two forces, main forces here, which is Fn and Ff and W. Those are the three forces here. Now do the same again as we did before, which is the sum of all the forces in Y, positive up, equals 0. There's no acceleration on the Y axis, so that means equal what we have. We have Fn and this angle here, again this is theta and this is theta as well. So Fn times the cosine of theta, this is this force here, and that's going up. What else is going up? Now FF is going up as well, so that means, remember that FF is equal the force, the normal force, multiplied by mu s. So what we have here is, in this case, it's going up, which is the up direction here for positive. That means plus Fn mu s times sine of theta. Now W is the only one going down, minus W equals 0. So we got that. So Fn is a common factor here for these two. So we have Fn cosine of theta plus, in this case, Fn mu s times sine of theta, close parenthesis, equal positive W. And now we have that Fn equal W over cosine of theta plus mu s times sine of theta. So we got that. Now what's happening on the x-axis, this x-axis here, this one? Well, what we have is, first of all, the normal force is the only one pushing the car down, so that would be this one here, this guy here. And that means that what we have for the x balance, the force balance on x, and let's say positive that way, equal what we have. So we have this force on the x, that would be Fn times the cosine of theta. So because it's sine of theta. Oops, sine of theta. There we go. Because it's this force here, which is, this is theta, so I'm breaking this force within this one. So that means sine of theta. And what we have now, what we have is, this is a little bit ugly, let's fix it. Theta, there we go. And what we have is this force on x, that means minus Fn mu s, because that's the friction force, but then cosine of theta. Any other force involved here? Let's see. On x, only we have is the Fn on this one, and we have this guy here, which has to do with the friction. So that has to be then equal to the mass to the normal acceleration of the car, or the centripetal acceleration, AN, or the normal acceleration, typically that's what we call it. So with that said, then how this gonna work for us is Fn is a factor, common factor, we can take it out, Fn, so we end up sine of theta minus mu s times the cosine of theta, close parenthesis, equal m an. Now Fn is the one as shown here before, so that's going to be W over cosine of theta plus mu s times sine of theta. Again, W we can say that is mg, and that multiplied by sine of theta minus mu s cosine of theta, close parenthesis, equal m an is b tangent velocity divided by r. There we go. M cancel it back again, and we end up like bt square equal, this r I'm going to multiply by r both sides, so end up being rg times sine of theta minus mu s cosine of theta, close this parenthesis here, divided by cosine of theta plus mu s sine of theta, and close this one, and finally all this one. Since it's the square root, I'm gonna take that, so let's say that we end up like this, and that will do. Again, interesting result. What's gonna happen if there's no friction at all? If there's no friction, we end up with the same result as one of our cases here when there was no friction on the other page. Let's see, let's bring the differences between both. There we go. Let's copy these. There we go. This is minimum velocity, and have a problem with my pen here, but bear in mind it does seem to have a problem. Minimum velocity and maximum velocity. So the difference is where the negative is now located. So it's plus for minimum end up being here negative, and now it's different. You see, it changed the position of the minimum. I'm also changed the who gonna bear. Let's see, we have mu s cosine of theta. We have negative mu s cosine of theta plus sine of theta plus sine. So it's okay here, except that this is negative versus this is positive here. Now the other way, the other thing is true. Sine of theta here is positive, but here is negative. Now, when you compare, I mean, this guy is the one that we are working right now. If you say that mu s for that is equal 0, then BT minimum end up being, when mu s is 0, this is gone, this is gone, this is gone, sine over cosine. So we end up having the same RG times the tangent of theta. So whether it's minimum or maximum, they're the same for that particular case, that mu s is equal 0. Now, when mu s is not 0, then it's going to be interesting what's going to happen at a given angle. Debating whether I'm going to plot this or not. In the particular case of theta equals 0, this is gone. Theta equals 0. This is gone. This is gone as well. But somehow we end up with a result in where it's not valid, because it's going to be a negative here, square root of a negative value. So when theta equals 0, this analysis is no longer valid the way I see it. Let's see. Theta equals 0. This is 1. This is gone. This is 1. This is gone. So you end up minus 1. You end up with BT minimum equal negative RG. For again, that's only when theta equals 0. So the theta, for this equation to be valid, theta must be or greater than 0. That's basically what it is. Not the case of the, on the other hand, the case went for maximum velocity. Theta just can be 0, but not on this one, which makes sense. I mean, the car can't fall down unless it's an angle on this Bankit curve. Now let's get some numbers. I want to see some numbers, some real numbers, and compare both equations, what they will do for us. Like, for example, if theta is equal, let's put a very steep bank curve here, 45. That's kind of interesting. 45 degrees, and let's say that mu s is 0.7. With those two parameters, let's figure it out. What are gonna be our result for an R? Let's say R equal 100 meter, and G obviously is 9.81. Anything else? Nope. That sounds super. Sounds like we got everything. So what is Vmax? Well, Vmax is gonna be square root of 9.81 times 100 times 0.7 cosine of theta plus sine of 45 divided by cosine of 45 minus 0.7 sine of 45, and Vmax equal, and sorry for the number, it looks kind of ugly, so I have a little bit problem with my Surface, doesn't run it right. It's very hot on the back of it, so somehow it's affecting the writing. Extremely hot. When it gets very hot, it gets kind of a, like very sensitive to auto writing. But anyway, so that would be the square root of 5559, and that is about 74.56 meter second. Wow, that's a very high speed. In miles per hour, very roughly, let's see, what would that be? In the neighborhood of 150 miles an hour, even higher than that. But let's give you an idea. That's meter per second. I don't want to convert that to miles per hour. You can do it yourself. But very fast speed. And these are the properties of the curve. Bank curve at 45, the static friction 0.7, R 100, G 9.81. So that's maximum velocity. Let's see what is the minimum velocity now. If we do minimum, minimum will be then pretty much the same thing, except that it's gonna be a negative here and a positive here, so definitely we'll make these numbers smaller. And let's see what we have. So that's 9.81 times 100 times sine of 45 minus 0.7 times the cosine of 45. Close that parenthesis, then go over here, and that would be cosine of 45 plus 0.7, and that would be 0.7 times sine of 45. I'm using this one equation here, and close our parentheses, go with this one and find out one here, and the whole thing is the square root. So b mean equal, let's pull the calculator here for a second. Alright, so that's the square root of 296.87. So b mean equal 88, to be sure, 88. 17.23 meters second. So that's the minimum speed, so that the car will not fall from the bank curve. You have to have a minimum speed because there's not enough friction to hold the car in place. So B mean is 17.23 meters per second. It's about 40 miles an hour or so. But then the maximum speed is way above 150 or somewhere there miles an hour. So that basically covers this kind of forces. Be sure that you understand where the centripetal force is being or act upon the car, so that we can work out then within that x, when that coordinate, the proper coordinate for that acceleration, so that you get everything right. And remember that the only forces here involved are W, and then the break of W within this normal force concept here shown here. But then you also have to break the friction, whether it's going up because the car might fall down, or the friction is going toward this direction because the car might get out of the bank curve. So you have to understand what are the analysis. In this particular case, the analysis was that if the friction is going that way, it's because the car might fall down, and that end up being what we call the minimum velocity that you can operate within this bank without falling into the ditch here somewhere. All right, so the other case is with maximum velocity, but that is kind of understandable because then the car will fall out of the higher point here and will get out of the road, so you don't want that. So that's why the friction is going the other direction. Well, folks, that's more than enough that I plan here to cover on these issues. So have a great day. Bye.